Welcome to this explainer. Today, we're going to build the absolute foundation of chemistry by exploring the tiny but incredibly mighty structure of the atom. Whether you're gearing up for exams or you just want to understand the fundamental building blocks of our universe, you are in exactly the right place. We'll break it all down step by step so you walk away with a rock-solid understanding. Let's get into it.
Here's our roadmap for today. We'll cover what an atom actually is, the three subatomic particles, the atom's internal structure, atomic and mass numbers, how to arrange electrons, and we'll wrap it all up with a quick quiz.
Starting right at the beginning with Section 1, what exactly is an atom? Take a quick second and just look around the room you're in. The screen you're staring at, the chair you're sitting on, the air you're breathing. Literally every single physical thing in your daily life is built from these microscopic elements. It's kind of mind-blowing, but atoms really are the ultimate Lego bricks of the entire universe. By definition, an atom is the smallest particle of an element that still acts like that specific element. But, and this is where it gets super interesting, they are not just solid, boring little spheres. They actually have this highly organized internal structure made of even smaller pieces.
Which brings us nicely to Section 2, the three subatomic particles. Let's meet the cast of characters inside the atom.
Notice the massive contrast here. We've got protons, neutrons, and electrons. Protons and neutrons both hang out right in the center, the nucleus, and they both have a relative mass of 1. Protons bring a positive charge, while neutrons, true to their name, are totally neutral. But look down at that bottom row. Electrons live outside the nucleus, they have a negative charge, and check out that mass, roughly 1 over 1836. They are practically weightless compared to the heavy hitters in the middle.
All right, Section 3, inside the atom structure. How is all of this actually arranged in space?
This is where the scale of things gets totally crazy. Picture a massive, packed football stadium. Now, put a single little marble right on the 50-yard line. That marble, that's your nucleus. It is incredibly tiny, yet it holds almost all of the atom's mass. The vast, empty space making up the rest of the stadium, that's the electron shells, where those lightweight electrons zoom around. The atom is literally mostly just empty space.
Moving into Section 4, atomic and mass numbers. Just like you have an ID card, atoms have specific numbers that tell us exactly who they are.
You're going to want to lock these two formulas into your brain. They're your ultimate survival guide here. The atomic number simply tells us the number of protons. That's it. It's the atom's identity. And if the atom is perfectly neutral, the protons will equal the electrons. On the flip side, the mass number is just the total of the heavy stuff. Since electrons weigh next to nothing, you just add up your protons and neutrons.
Let's look at an example to make it stick. Carbon has an atomic number of 6. That means a carbon atom always, without fail, has exactly 6 protons. And assuming it's neutral, it balances that out with exactly 6 electrons.
Now, using our other formula, a standard carbon atom, carbon-12, has a mass number of 12. Why? Because you just take its 6 protons, add its 6 neutrons, and boom, total mass of 12. It really is that straightforward.
We know what's going on in the center. So let's shift outwards to Section 5, arranging the electrons.
So electrons don't just swarm around randomly. They follow super strict seating arrangements, kind of like rows in a theater. For standard exams, you absolutely have to memorize these shell capacities. The first row, closest to the stage, is tiny. It only fits 2 electrons. The second row fits up to 8. And for the first 20 elements you need to know, the third row fits up to 8 as well. You always fill the inner rows completely before starting a new one.
Let's test drive this with a few elements. Oxygen has 8 electrons total. 2 take the front row, leaving 6 for the second shell. So its setup is 2, 6. Sodium has 11. 2 in the first, 8 in the second, that's 10, leaving 1 lonely electron to start the third shell. 2, 8, 1. Calcium has 20, so it fills out completely as 2, 8, 8, 2. Now, pay close attention to that very last shell for any atom. The electrons out there have a special name, valence electrons. This is a massive takeaway. These outer valence electrons are the ultimate deal makers in chemistry. Because they sit on the outside edge, they're the ones bumping into other atoms, which means they completely dictate how an element behaves and reacts.
All right, we have covered a ton of ground. Let's hit Section 6, a quick quiz and some tips to lock this all in.
Time to see what stuck. Question 1. Imagine an atom has 11 protons and 12 neutrons. What is its atomic number? Think back to our very first rule. Which particle is in charge of this?
It's 11.
Remember, the atomic number is literally just the proton count. The neutrons have absolutely nothing to do with it.
Okay, question 2. Using that exact same atom, 11 protons, 12 neutrons, what is its overall mass number? Think about the heavy nucleus here. It's 23, because our formula is simply protons plus neutrons. 11 plus 12 gives us 23. You're just adding up the heavy stuff.
Last one, question 3. How many electrons does a neutral sodium atom have knowing it has 11 protons? Remember the golden rule about electrical balance.
Yup, it's 11 electrons. To be perfectly neutral, those 11 positive protons in the middle must be perfectly balanced by 11 negative electrons zooming around the outside.
You guys totally crushed that today. But before we close out this explainer, I want to leave you with a bit of a brain teaser. What happens if an atom has the exact same atomic number, meaning it's the exact same element, but a completely different mass number? How is that even physically possible? Well, we're going to answer that massive question next time when we dive into the wild world of isotopes. Until then, practice drawing out those electron shells and happy learning.